Hey guys, today we're going to be learning about the activity series, and I'm going to be introducing you to the idea of standard reduction potentials, or E of reduction. We're going to connect this to oxidation and reduction that we've been learning about through the rest of the unit. So let's go ahead and get started. First thing I want to remind you of is reactivity. Now, we talked briefly about reactivity when we were looking at the periodic table trends in the first unit, or in the summer unit. These are going to be representative of both metals and nonmetals, and each different form, metal or nonmetal, has a different type of reactivity. Metals tend to react by losing electrons. Nonmetals tend to react by gaining electrons. So when we talk about reactivity, we're going to have to first identify whether we're talking about a metal or a nonmetal. If we're talking about a metal, the more reactive metals are the ones that more readily give up electrons, the ones that have lower ionization energies. And if we remember, that means that these are the ones with lower effective nuclear charges or greater numbers of energy levels. So going back to Coulomb's law, remember, it's charge over distance. Distance represented by the number of energy levels and the atomic radius. The bigger the atom is, the easier it's going to ionize or give up those electrons. For nonmetals, it's exactly the opposite. For nonmetals, the smaller atom is going to have a greater attractive force on those outer electrons, and therefore it will end up with a more reactive nonmetal because it more readily gains electrons. So if we look at the metal versus the nonmetal, this is a key factor. We need to make sure we're accounting for which type of atom are we looking at before we try to assess its relative reactivity. Normally, we're looking at metals. So today what I'm going to do is I'm really going to focus in on the reactivity of metals, and then we'll talk about nonmetals only a little bit throughout the course of the video. We can qualitatively show how reactive different elements are compared to each other on something we call an activity series. Now, an activity series is simply organized such that the more reactive element is going to be higher and the less reactive element is going to be lower. In the case of metals, this means that the higher you are in the activity series, the more readily you oxidize because you're more reactive. The lower you are in the activity series, the less readily you will oxidize. Now, this all comes back to probabilities. I don't want to talk about things wanting to oxidize or not wanting to oxidize. What I'm talking about here is simply it's more likely that it will oxidize the higher it is on the activity series. So if I'm comparing two things on the activity series, what I will say is the thing that is higher is simply more likely to react, or in the case of metals, oxidize, than the other. Now, we can use the activity series to help us predict replacement reactions, specifically single replacement reactions. If an element is more reactive, it is more likely to oxidize than the other thing. So what that means is that if we have a reaction between a more reactive metal in its elemental form and a less reactive metal in its ionic form, the single replacement reaction will happen spontaneously. This is a critical idea. Not all reactions are going to be spontaneous. If I were to take a solid of the metal that's lower on the activity series and place it in an ionic solution of the metal that's higher on the activity series, no reaction would occur spontaneously, and the two elements, or the two atoms for that matter, would end up retaining their same properties throughout. Now, one thing you'll notice in most activity series is that hydrogen is involved, even in the activity series of metals. Part of this is because, and we'll talk about this in a little bit, but many of the values of reactivity that we use quantitatively are based off of a hydrogen's ability to oxidize and or reduce. So we use hydrogen as kind of our baseline. Kind of like the freezing point of water is the 0 degree for Celsius. The hydrogen ability to oxidize or reduce is going to be the 0 for our activity series. In order to be able to predict whether a reaction will occur, we need to be able to look at what the products would be and then look at the activity series to predict whether that reaction will proceed spontaneously. Spontaneously means we don't have to add any more energy to make it happen. So for instance, in this reaction where I'm taking potassium in its solid form and reacting with sodium oxide, what I can do is, first of all, predict the products, and then, based on the activity series, predict whether the reaction would happen or not. So first of all, in this single replacement reaction, we'd end up with sodium solid and potassium oxide. Now remember, if you are going to be more reactive as a metal, that suggests that you're more readily oxidized. Because if we look at the products, the potassium would have gone from elemental form to its ionic form. It would have been oxidized. And because potassium is higher on the activity series, therefore more reactive, it will more readily oxidize than the sodium. For that reason, this reaction would be considered spontaneous. Therefore, if we were to actually perform this, where we put solid potassium into sodium oxide, we would actually see solid sodium formed and potassium oxide formed. In addition to the activity series, you're actually going to be able to quantitatively show whether a reaction will be spontaneous or not. We're going to talk more about this when we get to electrochemistry, but at the very least I'm going to introduce you to the concept now. And that concept is called a standard reduction potential. Standard reduction potential is shown as the letter E, capital E, with a subscript red, or reduction. What this tells us is quantitatively how much of a probability there is for this one thing to be reduced. Remember, the activity series for metals was based off of oxidation. The reduction potentials, however, are based, as the name suggests, off of the reduction. If a metal is more reactive, what that means is that a more positive E of reduction value, or a larger value, suggests that, in fact, that element is more likely to go through reduction than oxidation. So what we can do is, similarly to the activity series, where we compared whether something was above or below on the activity series compared to another, we can also do this in an E of reduction situation. If the thing that is being reduced in our reaction, or that we would predict to be reduced in our reaction, has a more positive E of reduction, that reaction will be considered spontaneous. If that element that we think is going to be reduced is going to have a less positive E of reduction, then the reaction would be non-spontaneous, and the reaction would not go to completion, or for that matter, even be able to continue without additional energy being added to it. Now, I'm talking about E of reductions, or its relative likelihood of being reduced. There are also things called E of oxidations. E of oxidation is literally the opposite of E of reduction. Opposite in the sense of I'm flipping the reaction. So instead of it gaining electrons, I'm not talking about it now, losing electrons. And the way we are going to handle this is by taking the sign of the E of reduction and simply putting a negative in front. So if it was positive as an E of reduction, it becomes negative as an E of oxidation. If it was negative for an E of reduction, it becomes positive for an E of oxidation. What this means is the more likely something is to be reduced, the less likely it is to be oxidized, which makes sense. So if we look at this table of E of reduction values, and by the way, this is oftentimes how you're going to be shown. You're going to be shown a series of E of reduction values, and you're going to be asked various questions about them. One question is, which is the most likely to be reduced? So if we look at these E of reduction values, we're going to look for the most positive E of reduction. That, in this case, would be the reduction of the silver ion, Ag+, adding one electron to produce silver solid, fully reducing that silver ion. So if we reduce silver, it's going to have an E of reduction value of positive 0.799. No others are as positive as that. That means that the silver is more likely to be reduced than any other element that we see here. We can also predict whether reactions would occur in groups. So here I've got a table that represents whether or not reactions would occur given each other's relative E of reduction or activity series values. If a reaction is going to show a replacement, that means the thing that is replacing the other. So for instance, if we have a solid replacing an ion, the thing that is in the solid form must be oxidized, and the thing that's in the ionic form must be reduced. So if this is going to happen, then the thing that is replacing, or the thing that was in its elemental solid form, must have a more negative or less positive E of reduction value. If it does not, then the reaction would be non-spontaneous. So let's take a look at this table and make a prediction as to what would happen. So we've taken a look at it. Now, if we look at this, notice how the metal of A, that means the solid form of A, did not react with either B or C in their oxide or ionic forms. This means that the A element is least reactive. Least reactive means it was the least able to oxidize, or the least likely to oxidize. This suggests that instead it has the highest E of reduction value. The most reactive in this situation was B, And the reason it was B is because we can see that the metal B replaced both A and C within their individual reactions. So this is actual evidence from reactions telling us the relative reactivity of different metals. So sometimes you might be asked to rank metals based on their relative reactivities. This is one way we can do that using empirical reaction-based evidence. Now take a look at this problem. I'm asking you to rank relative reactivities of these metals based on their E of reduction values. Be careful. Remember, reactivity of metals means oxidation. E of reduction tells us something slightly different. Take a look, give it a shot, rank them, and then we'll talk about the answer in a second. The aluminum would be the most reactive, followed by the zinc, then the chromium, then the nickel. The aluminum we would consider the most reactive because it had the most negative E of reduction. And remember, a negative E of reduction would suggest that it's more likely to be oxidized, because if we flip the sign, it's actually a more positive E of oxidation. Be aware, the more likely something is to be oxidized, the less likely it is to be reduced. So, the aluminum, therefore, is the most reactive because, as with metals, it's more likely to be oxidized. Now, be careful, because remember, we talked about a general trend of reactivity, but obviously aluminum kind of defies that. We would expect aluminum, based on its position on the periodic table, to be less reactive as a metal, but instead it's more. Why? Well, a lot of it has to go with nuances of how electrons are added and removed into atoms as they become ions. So be careful. Yes, we can have general trends, but you have to use the empirical evidence that you're given to prove or to show the trends, whether they are correct or not. And you cannot ever simply in an answer respond with, because the periodic table trend shows that we would be more or less reactive. That will never fly, even if you are correct in your statement. So that wraps up today's video. Let's do a quick recap. Today, we looked at relative reactivities and two ways that we can qualitatively and or quantitatively assess relative reactivity of metals or nonmetals. The qualitative manner was with an activity series, where the higher you are in the activity series, the more likely you are to react. And then quantitatively, we looked at E of reduction values, where the more positive you were as an E of reduction, the more likely you were to be reduced. We looked at this relative to the likelihood of a reaction being spontaneous or not, and we did some example problems to show it. I'd like to thank Olvia Blukos for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one.